Hello, mathletes. Hope you're having a great day. So, still in 3.1 here, and we're going to talk about instantaneous velocity, which is another basically physical kind of representation of what the derivative is. And we've talked about this before, but let's be a little more. Let's get a little more in depth with this scenario. So we have our position function, which is s of t. So that's a position of an object over time, right? So y is some distance basically that an object is away from a certain fixed location, and then the horizontal axis is time. So over time, what happens is we have this object that starts out at this point, some distance away from it, like I said, a fixed location, and then it starts traveling away from that, and it travels away, and it kind of starts leveling out here, and then it actually starts kind of going back towards whatever that location was, that fixed location, as it goes this way, right? And so that's what this particular curve does. All right, so it goes away, and then it starts returning, and as it goes towards the horizontal axis, that means it's getting close. It's now getting closer to where it started, right? Okay, and so what we're trying to do is, we're trying to find out what the rate of change is at any given point, right? And before we've dealt with the secant line, and so the secant line here is an approximation of the rate of change, right? Of the instantaneous rate of change. It's the average rate of change. So the slope of the secant line from here to here is the average velocity of that object from point A to point T, right? Okay. And remember that if I want to find the slope at this point right here, then if I can get this secant line, if I can get a point closer to the point where I'm trying to find the slope, and I draw a secant line there, that'll give me a better approximation. I should do it here, actually, sorry. That'll give me a better approximation of the instantaneous rate of change, or the tangent line, right? And the closer I get to this point, the more accurate our line will be, right? The closer the secant line will be to the tangent line. And so remember that our new formula says that the slope of tangent line is equal to the limit as, and we have a couple different formulas, but here we'll use the one that's the quotient, or the difference quotient, and that's the one where we have f of, in this case we'll use x. So f of x minus f of a all over x minus a, right? And here we have t instead of x, so we can put t in for x. But anyway, so this is our formula, right? And as x gets closer to a, right, as this value gets closer and closer to a, our secant line is going to get closer and closer to the actual tangent line, right? To the point where it actually is going to be the tangent line. Okay, and so this is the formula that gets us there. And remember that the slope of the tangent line is also equivalent to the average, the instantaneous velocity of that object at any given point. Okay, and so if we can find the slope of the tangent line, that'll tell us the instantaneous velocity. And so therefore, the instantaneous velocity at a point is equal to the derivative at that point. All right, so back to the line. Remember that, like we talked about in the Kahoot the other day, is that what we can tell about the slope of the tangent line, or about the velocity, is if the object, or if the line is going up to the right, up as it goes right, then it's going to be a positive slope, right? If it's going down as it goes right, it's going to have a negative slope. If it levels off, it's going to have a zero slope, right? So somewhere here, there's a zero slope for this line. That means the object has a velocity of zero, right? So it has to stop and turn around and go the other direction, right? And that's what happens. And so the steeper it is, the larger the absolute value is going to be of the velocity. Okay, and as it gets shallower and shallower, the lower or the smaller the absolute value is going to be of the velocity. Okay, so steeper means it's going faster, right? It's traveling away from a certain object at a higher rate. As it levels out, it's slowing down, slowing down, slowing down. It's going to get to zero, and then it turns around. Now it's going back towards where it came from, and so it has a negative velocity if it's going in the opposite direction. Okay. All right, so this is motion, and remember this is a position curve, usually S of t, sometimes they'll call it X of t is the position curve, and then V of t will be our velocity, curve. All right, so, and then later on we'll even talk about A of t, which is our acceleration, and acceleration is the rate of change of velocity, right? How fast is your speed increasing or decreasing, right? Velocity is how fast is your position increasing or decreasing. And so we can take both of those things and just remember that the velocity function equals the derivative of the position function. Okay. All right. And we also know that the acceleration function is the derivative of the velocity function. All right. So basically it's saying velocity is the rate of change of position, the instantaneous rate of change of position, and acceleration is the instantaneous rate of change of velocity.